So just to give some idea about what you should expect from the material today is some basics about cloth rendering for beginners, and then some types of representation for fabrics, advantages and disadvantages, previous solutions, and some state-of-the-art solutions that has been done, majority of them by myself and my collaborators. And the audience are anyone as a student or beginner. We have industrial friends, and then researchers, or technically anyone would enjoy. So the arrangement of the talk today is that we first start with some basics like Cloth 101. We will next go to some rendering models for fabrics, and then we will end with more recent ones, which are the ones that I've been working recently. But what should we care? Why should we care about cloth rendering in the first place? And the answer is because we are not there yet. These are some digitally made cloth, and they still have some issues. For example, the fibers are too few and too hard, or the cloth still looks too thick. So the artist wouldn't appreciate the realism of the fabrics that we can generate with the existing cloth models. Or they are still far from photorealistic. For example, an artist wants to change the metallic or anisotropy or some other parameters from a fabric, and they expect to see something that follows what they want, but production tools that we have at the moment are not there yet. So that's why we still care about cloth rendering, and there are still research in this direction. The key to cloth rendering is the structure of it, and that makes it very hard, because on the left you see the structure in micro level, and on the right you see how it turns up in the far field, in a distance. And the structure matters, and that's why it makes it very hard to reproduce fabrics in digital world. There are different levels of cloth geometry, and that is why it is challenging. For example, we see a woven cloth on the left, but the underlying structure is technically what you see on the right. So we have to model it digitally in that level in order to get the same realism on the left. And the fun part is that even the single fibers are not smooth, what you see on the right. So it's a very, very hard part in order to, if you want to reproduce fabrics digitally. And when we talk about the cloth structure, the other thing is a hierarchical structure that we see in a single yarn. So for example, here we see a single yarn, which is like a cylinder. And then each yarn consists of multiple plies, and each of those plies consist of hundreds of fibers. And then arrangements of these yarns can make woven cloth or knitted cloth. These are the two most common types of cloth that we do. And then once you have the actual cloth, you can make it into a woven like this. We have warps and wefts going in the vertical and horizontal direction, and then more complicated directions to make some knitted fabrics. So these are the fabrics that we are most interested in. Let's talk about woven for a second. Woven fabrics have these binary pattern map that we say, where they show where the yarns should follow. Basically, the green ones are the warps, and the other ones are the weft. And then you can see on top, the rendering of each of these fabrics would look completely different just because of the arrangement of these yarns are different. And for knitted one, these are more common in manufacturing, and a lot of shirts and sweaters are knitted ones. And usually the yarns are thicker in this type of fabric, and that's why the thickness of the yarn is another parameter that we have to be able to digitally tweak. One of the effects that is very challenging but very interesting in fabrics that we want to reproduce is this called sheen effect. When you see on the edge, it's brightened up. So this is a fabric specific effect that we get. So we have flyaway fibers as well, when we have some strands of fibers that are sticked out of the cloth, and that they are called flyaways, and they help the realism by a lot. And the other fact that is very important to make a cloth look like cloth is the shadowing masking. And the reason it's challenging to capture is because imagine these are the yarns going vertically, and this is the horizontal one. And then when we see it from part of these cylinders would be visible and part of it will be shadowed. And then these has to be digitally reproduced in order to get the exact shadowing masking. Otherwise, the cloth would turn up dimmer or brighter. Another effect that we are interested is the anisotropy effect, because when you see the cloth from different directions, you see they appear differently. For example, the top one is the exact same one, the same material as the bottom one, is just 90-degree rotated, and you see how different they look. So this is another feature that makes cloth more challenging to reproduce, but this is one of the features that, again, it's fabric specific. We also have transparency in cloth. For example, here on the right, we see the light source in the back of cloth and how the light transmitting through the material. And this is also quite challenging, but again, interesting. And lastly, we have the details and the variation of the fabric, because they are very diverse. And that's basically makes it quite challenging to reproduce. This is possible to make the cloth look like a real cloth, but the challenge is the speed, because we would sacrifice the speed over accuracy. All right, so this was all about the basics of cloth that I wanted to build before we get into some cloth rendering models. So next we're discussing about the actual models, which are divided into two main categories. One of them are micro appearance models, and the other are surface-based models. For each of them, we have the geometry and the shading separately. So let's get started. The first one is a volumetric representation. Essentially, we can start with micro CT scan images. So technically, it's a super crazy data that we CT scan a cloth, and then we reconstruct the density field, the orientation field, and then we do the appearance matching with a real fabric, and that's how we end up with an actual rendered result. But this is, of course, super crazy in terms of memory or rendering time, but very accurate. This is an example of a rendered image. So as we said, they are extremely realistic, because but one of the disadvantages is that they require CT scan imaging, and also they have terabytes of data, which is quite expensive to generate. There is this accelerated volume representation was proposed same year, that basically they use some subdivision in order to make some coarse grid, and that makes it accelerated. But the disadvantage for this model is that there's no near field, so you cannot zoom in technically. And the rendering is still not very efficient. So it is better than before because of the storage has been upgraded, but the speed hasn't. And in terms of the shading part, so this was about the geometry part of the volumetric representation. And for shading, there are these two main models that people use. It's either microflake model or SGGX model. I don't want to talk about them in detail, but just a quick note about how we shade them. So now let's move on to the fiber level geometry. This means that we have all fibers technically as curves represented into the model. So instead of a volume representation, now we have curve-based representation. One previous work basically divided the fibers into regular fibers and the flyaway fibers. Flyaways, those that are basically make this fuzzy effect. And then we have very, very realistic appearance using them, but again, they have terabytes of data to be stored because all these curves need control points, and they are very hard to match with real world, so it's very hard to edit as well. So again, they have their own disadvantages. And then later we got this new work on procedural fiber generation. So technically, instead of storing every curve, can we make everything procedurally? So again, it would reduce memory, of course, but the rendering is still insufficient. And we still need to ray trace all these fiber geometries. So that's the disadvantage of this fiber level model as well. And on the shading side, again, we have the geometry of a fiber. Imagine this is a single curve in the center. And then how do we shade it? And in that scenario, we have this model which proposed an idea of this cone representation and two components, one for transmission and one for reflection. And this is how we can shade a single curve. Again, they may look accurate and realistic, but the disadvantage comes in memory and time, which is too crazy. So now let's move on to the more simple one, the surface-based representation. By surface-based, we technically mean starting with a base mesh. It's like a 2D triangulated mesh, so it's much, much lighter than volumetric or fiber-based distribution. And it's very highly used in industry. For example, what they do in industry, this is the rendering, and then they split it into diffuse and a specular component, and this is technically a mesh, that's it. So it's quite fast. And these are more examples that used in game industry, and how we can see on the right the cloth has good enough of features like all these sheen effect and whatnot. So now this is one of the surface-based models that I want to talk about. This is one of the first ones, Irvine et al. And the way that they represent it is that we actually model these yarns going vertically and horizontally. And then at every point along that, we find a tangent direction. And that gives us basically how they arc around and how it reflects light. So that would makes it pretty cool, because then we can get actually the binary pattern into account. But they only do the reflection. So we cannot do any transmission with this, but we can roughly match the reflection. So this is the photo, and then here is the rendered image, and which we can do a good enough a job with this model. And next model was Sadeghi model from 2013, where we can actually get we can actually define the cloth as parameters. So we can actually define the warps and wefts and the direction and their widthness and their thickness, and that way we can get it more accurate. But the problem is that we cannot zoom in. So if you zoom in, you don't see exactly the yarns, because everything has been aggregated, averaged out. So that's the bottleneck. There is no near field model for this. And this model called macrocylinder, and this is very useful in computer games, but they don't do near field. They only do far field. So all these surface-based models that we discussed, Irvine model, Sadeghi model, or DreamWorks model, they are very fast in terms of memory and time, because technically there is just a mesh being stored. but they don't look good enough. They don't look realistic enough, especially if you zoom in, you don't not see the detail. You basically get everything blurred out. And they only do the reflection, but we don't know what happens if the light passes through them. Another paper that came the year after was this real-time one, when we can split the model, the fibers into the core fibers, and we can also do the multi-resolution, the level of detail, and so on. And this allow some detail, because technically you can see all these fibers, but the focus was only on cloth knitted ones and the knitted fabrics, and they don't do any shading model. Technically, it's all about geometry, and although it's real time, they allow fiber details, but they don't propose anything what we do on the shading side. So later on, we had this model when we can do a real time, and we also add the flyaways this time. But again, what we do is only the reflection. We don't know what happens when the light passes through the cloth, and that's still a challenge to be solved. As an ideal model, what we want is not only being accurate, but we also want a memory efficient, fast to render, and we want something general for all cloth. And that gave us the idea of reducing the number of fibers, because that's basically the bottleneck. And that's how we got into this aggregated base models. And my paper was one of the first ones, that what if we do some aggregation. This is from Zhu, that we have the level of detail technically when we have fair is very similar to fabric, by the way. When we have these single fair, it's very similar to single fiber. So it's the shading model is the same thing. They borrow the same model. So this one on the right, top left, is the aggregated model, and the top left is when we do the aggregated but just averaged out. So if we just do the original fibers to be averaged out, they look drier, harder, and brighter. But if we aggregate them, what is in this corner, we get the realistic. So this was an aggregated base model. And that turned up all new models in the last few years. So this is my paper when we talked about ply-based representation. So essentially all these tiny circles are fibers. And then we aggregate all these fibers into one single capsule. And then this is how we do the geometry silhouette. And on the shading model, we again have some aggregation lobes. So these 4 lobes are averaged out of what would happen if the ray would hit inside the fiber. So essentially this whole bundle is a ply, and all these circles are fibers. So we don't care about what's going on inside. We only care about this encapsulated cylinder around it. And we can get good enough of an appearance. This is the results comparing to the reference on the right. We can offer same level of appearance. And in this way, we can do very quick rendering. But the what the drawback is that it's artist-driven. It's not very physics-based. And if we have a lot of plies, then it's also not very efficient. And then we came up with a different approach where we can do this all analytically. So on the geometric representation, we keep it the same. We have the plies, aggregated fibers. But on the shading model, we do everything aggregated. Basically, we analytically integrate the fiber representation into a yarn representation. By that, I mean, if we have, this is the longitudinal and azimuthal view of a yarn. So this is a cylinder, this is a yarn, and then there are hundreds of fibers inside them. How can we do an averaged representation? In this way, we use dual scattering. And we call it extended dual scattering because we have some improvement into it. But dual scattering was a technique before that was useful for subsurface scattering. So we basically came up with a updated version where we can do the forward and backward scattering and how we can approximate it that way. And this is a result that so for us, we expected to not see the individual fibers, of course, but we expected to see the highlight turn up in the correct position. So for example, this highlight on the right of the yarn should appear correctly on the right. Even if we change the density, it works roughly the same. Or if we change the twist, we still get the same thing. So although it's in the yarn level, we don't expect to see the fiber details, but the overall appearance matches what we want. And this is the same idea, we can do it in the ply level. So we can aggregate the ply level. So remember, we have fiber, ply, and yarn level. So we can go one step higher and do the same aggregation using dual scattering. And again, we get the same result. So this is multiple ply yarn, and then we get the same behavior reproduced by our model. And in the far field, it's very hard to distinguish between the reference and ours. But of course, in the close-up on the left, we don't see the fiber details, but this doesn't meant to work in the near field. And then later we had another paper when we moved not only from ply level, but now in yarn level. So basically we aggregated another level. And this way we now have not only multiple plies aggregated, but also the multiple fibers aggregated. And then they are encapsulated into these components, these four components. And this, as a conclusion, we just wanted to share how we can produce accurate and fast models, and they are also very much memory efficient compared to the existing works. They are physically based because everything is follow physics. It's a model works for woven, for knit, for any pattern, so it's general. They are very easy to edit, but how about if we can do better, but we still have room to improve? Can we do even better? So that brings up to my last part of the talk, and here's the overview. We start with state-of-the-art surface-based models, so basically that's pretty much where we left off. And then we would discuss how we can do the reconstruction. By reconstruction, it means that you have a photo of a fabric, can you reproduce it digitally? So now let's start with realistic appearance model. And by realistic appearance model, we look for realism, for storage, for performance, also for reconstruction. And as a state-of-the-art example, we start with this paper from 2 years ago. This one it has the realism. It accounts for complex visual effects. We start with a photograph, and then this is the level of accuracy we can reproduce. We can also do the transmission of the light. So imagine there is a light source in the back of fabric in all these 4 examples, and then we can reproduce them on the bottom. So this is also working for transmission component, which was neglected in pretty much all previous works. We can also do the transparency. This is about how the light directly passes through a fabric. And then this is about the detail, where we can do the yarn shading. Can we zoom in and see individual yarns? And then this is a rendered image to match with this photo example. So here's the same material on a mannequin and how we can reproduce the similar appearance. And the other feature that is added compared to the previous work is this noise thing that makes it much more realistic because of the irregularity. And then we have the shadowing masking, as we discussed before. This is important. And if we don't have that, the edges look much brighter than what they should. So this is another feature that we discussed at the beginning, how important it is, and it was missing in the previous work. And then this is just an example of our rendering. Now let's discuss about level of detail. By level of detail, we mean, can we zoom in and we still see proper detail, or is it gonna just blurred out? So this is the level of detail we expect to see when we zoom in. And of course, it would require high sample per pixel. Otherwise, it's gonna have a lot of fireflies, but that's where the problem is. That's why we need a multi-resolution or a multi-scale problem. So instead of using 1,000 samples per pixel, which is the current models, can we do it just with one sample, and we can still the same level of detail? So this is a preview of a model, and on the left we see all these models, all these parameters can be tweaked. So the other way we can do the level of detail is using a neural approach. To do so, we can basically have an encoder to pass all the geometric map and the shading parameters into this latent. And then we have a decoder that gets the view and the light and the footprint, and then spit out the actual BSDF or BRDF, which is the RGB value of that pixel. So this is another way to do the level of detail. And what I wanted to share here is that we can do it general enough for all different patterns. So we have plain, twill, satin, and whatnot. So basically works for anything. It's general enough for everything. And it's also efficient. We can do it by real time. And the way that that can be done is by decomposing the specular and diffuse component further for every warp and weft, and that makes it quite fast and efficient. And here is just a result of the paper, how we can do both close up and far view, basically far field and near field, and both works pretty good. So this is when we talk about a multi-scale model. But the limitation is that we cannot do flyaways for this particular model, and this fuzziness that we see on the edge, or also some repeating feature is appear because we don't have enough irregularities. So that makes that's essentially the limitation, which is shared with a lot of works in this direction. A lot of them are pre-computation based, and what we discussed, they need texture. So that's basically, in order to generate those texture, you need to pre-compute something. And they may also be neural based, and the last one that I showed. So these are the limitations which are will take me to the next part of the talk, which is the reconstruction. Can we reconstruct a fabric if we have a photo of a real fabric taken? Can we reproduce it virtually? So it's a very hot topic because a lot of applications in AR and VR require us to take a photo, and then you want to have a full body digital avatar of it. And the ultimate goal, in order to get that, essentially, this is what we get as an input on the left. We want, I'll just read it out, rapid and automatic appearance reconstruction from sparse in the wild sensor data that can be rendered under novel geometric deformation. So imagine you stretch the fiber or something, with a novel viewport, technically moving the camera, under novel lighting condition, or imagine you change the light condition, light rig, while support appearance editing, and this is editability of a model, and ideally in real time frame rate. So this is the ideal scenario of someone defining what we want. So as an example, we can start with this particular paper. When we start with this photo on the left, which has been taken by just iPhone, and then we reproduce them virtually, which is a good enough of a match. And we use differentiable rendering here. I don't know how many of you are familiar with that, but technically, if you have continuous space for parameters, you can get the differentiation of the parameters and optimize it that way. So basically, we also have neural approach in order to match the target image into ground truth parameters. So that's what we do. And then later, there are some works on generative AI. Technically, we have GAN model or diffusion model, where we can reconstruct an input image by splitting it into these maps. For example, this particular paper is an RGBX paper, which is quite interesting, where we can convert RGBX in RGB, which is an input image, into X, which is called G buffer. And by that, we mean albedo, normal, roughness, metallicity, iridescence. So you are technically split it out via a diffusion network. And then you have a second diffusion network where you are decoding it back into a synthesized image. And this way, we can learn how to generate images directly following text prompts. So here is an example of the text prompt. For example, we have a colorful sofa, and then we get out something completely different from so the thing is, like any other diffusion-based models, if we use the same text a few times, you would get different things. That's the drawback. So now let's move on to data-driven reconstruction. So in data-driven reconstruction, you actually have point clouds being captured. So everything has been measured. For example, you can use 3D Gaussian splatting in order to fit your model. And this is, of course, data-driven. You can do novel view synthesis because you have basically the control point of the whole object. So you can move around, and it's good for volumetric representation for fabric, because again, you have the whole 3D representation of it. And these are two example papers doing the same way. And then lastly, what I wanted to talk about is this learning-based approach, where you use 3D Gaussian splattering. And here we do a pose dependence. So it basically learns about different poses, and then we can use local geometric info, and then we given a video sequence from all around an object, then we can spit out the actual rendered image. So again, it works if you have different view direction, but it would mess up if you have different lighting, because then the material is changed, and they are not editable as well, which is in common with all other methods in neural-based methods like NERF or Gaussian splatting, where they are not editable. So that's the bottom line. As a final note, I also wanted to discuss this last paper, where this is also pose dependent, but they also have this video where goes around an object, and then we do this intrinsic parameter, which instead of, so that's the difference with previous model, where we have this normal albedo, roughness, and visibility. And then those are passed to the network, and the network learns about those maps separately. And then after all, it basically spits out all these, which we call G buffer, and then they are good enough to render something. So that's how you can reconstruct from an input photo taken to reproduce them virtually. But as a limitation for these data-driven approaches, first of all, they need lots of data. You do need to capture them. They are very slow for reconstruction. They are, of course, not easy for editing because all you can reproduce is the exact same material. So you cannot change the model. You cannot change the material. And the visual quality is not thoroughly analyzed. We can still do better, especially when you zoom in, it's quite blurred up, very similar to NeRF model or Gaussian splatting. It's very hard for the qualities, especially in close-up. All right, so that was it on the data-driven as well. So that concludes my talk. I'm happy to take questions.